Hebgen Lake area northwest of Yellowstone Park. The night of August 17, 1959 was clear and peaceful. A full moon rose over the valley and quiet settled over the forest as vacation campers settled down for a night's sleep. They were not aware that the valley lay directly over a fault in the Earth's crust. Suddenly, at about 11:30 p.m., 3 blocks of the crust shifted, and the resulting earthquake shattered the stillness. Cabins collapsed into rubble. Landslides buried campgrounds and destroyed roads. Falling rocks uprooted trees. Attendants at the dam watched in amazement as the water in Hebgen Lake began sloshing back and forth. The first few surges of water were so high that they flowed over the dam. There was great concern that the dam itself would give way. In a matter of minutes, changes came to the Madison River Canyon. Changes that are a part of the continuing story of movement in the Earth's crust. The movement of great crustal blocks, like the one that occurred here in the Hebgen area, is not unusual. We know that sections of the crust may swell as magma moves through volcanic channels, and that gigantic forces within the Earth are constantly pushing up mountains. But these movements are very small and very slow, almost imperceptible. As they reshape the surface of our planet, we humans see very little evidence of that change. Earthquakes result when crustal forces build up great stress that is suddenly released. In the Hebgen Lake area, the underlying layers of rocks had been gradually bent and folded over millions of years as the Rocky Mountains were formed. The tremendous pressure eventually broke the rocks, pushing one group over another, creating a thrust fault. Forces that had been previously pushing the rocks together then began to pull them apart. As the rocks were pulled apart, gravity caused the blocks on either side to shift abruptly, and the result was an earthquake. The Hebgen quake didn't happen all at once, but was divided into a series of small drops. Each drop of the block created a separate earthquake, and the results at the Earth's surface were spectacular. The vibration shook loose hundreds of boulders high on the valley walls. They bounced and crashed down the hillsides, flattening the trees in their paths. Part of the highway through the valley disappeared beneath the lake. Giant slabs of concrete were broken like matchsticks. Cabins were shaken off their foundations. Those at the water's edge sank into the lake as the block shifted, while across the lake the land rose, leaving boats and piers high above the water. The earthquake caused the water in Hebgen Lake to slosh back and forth like the water in a bucket sloshes when you shake the bucket. This backward and forward sloshing continued for 12 hours, with each slosh taking about 17 minutes. Where small faults occurred on larger blocks, scarps like this one marked movement along the break. This block dropped almost 5 meters. The area was a campground, and one very surprised camper awoke to find his tent up there and his fireplace down here. Yet the most awesome damage of all occurred downstream. The loose, weathered rock at the top of one side of the canyon began sliding into the Madison River, 29 million cubic meters of rock, enough to build a two-lane highway from Montana to New York, slid down the valley wall. The mass of rock rode almost 120 meters up onto the other side of the valley, and then slid back toward the bottom. A new lake formed behind the slide as it completely blocked the Madison River. The sudden rush of wind produced by the slide as it traveled downward literally blew some campers away. Others survived by hanging onto trees. Boulders the size of houses were scattered in a huge pile of debris. "28 people lie buried beneath the slide, but if this earthquake had occurred in a more populated area, the damage and loss of life would have been much greater." The earthquake in the Madison River Canyon was felt by people living nearby, but it was recorded by seismologists around the world. The instruments they use, called seismographs, are designed to measure vibrations traveling through the Earth's crust. This seismograph consists of a large mass attached to a coil of wire and suspended so that it can move freely between the poles of a large magnet. When the Earth shakes, the magnet moves with the crust, but the freely suspended mass tends to stand still. So the magnet moves around the coil and generates an electric current that can be recorded. This seismograph can record motion only at right angles to its pendulum. Another one, that records vertical motion, must be used to obtain truly accurate records. Scientists try to place seismographs away from highways and other sources of vibration. They often locate them underground on concrete slabs attached securely to the Earth's crust. Modern seismographic installations use 3 instruments: one for north-south, one for east-west, and one for vertical motion. These recorders are making a continuous record of the seismic activity in the Earth's crust. The paper charts, called seismograms, are changed once each day. Seismologists study the records of earthquakes preserved on seismograms in an effort to learn more about the Earth's interior. They have learned that there are 3 types of seismic waves. The first is called a P wave and travels rapidly through the crust, creating a push-pull effect on the rock as it passes. The S wave moves more slowly and is called the shear wave because the crust moves at right angles to the direction of the wave. On this seismogram, we can see that the P wave is the first to be recorded, and here, seconds later, is the S wave arrival. A third type of wave, called the L wave, is a slow wave that travels along the surface and is the one responsible for most of the destructive force of an earthquake. The different behavior of the waves is useful to seismologists in studying the properties of earth tremors. The difference in speed of different types of waves allows them to determine the distance between their station and the point on the Earth's surface directly above the earthquake. That point is called the epicenter. The earthquake that shook the Hebgen area measured 7.1 on the Richter scale, a very strong shock indeed. The Richter scale is a measure of the energy released by the quake and is determined by measurement of the seismograph records. Earthquakes are very common on our planet. The red dots on this map mark the location of strong quakes around the world. Earthquake activity is concentrated where one crustal plate meets another. Along the Pacific coast, up the Canadian coast, and across Alaska, the North American continental plate is in collision with the Pacific oceanic plate. In 1964, 1/3 of the state of Alaska was jolted by 3 earthquakes of magnitudes 5.5, 5.6, and 5.9 that destroyed Fairbanks and Anchorage. Large ocean waves called tsunamis were caused by these quakes and added to the destruction as tons of water swept inland. Such seismic sea waves are generated beneath the ocean and are a special menace to low-lying coastal regions. While the problem of predicting their occurrence has not been solved, the work goes on, and scientists continue to be fascinated by earthquakes. For simply learning to predict their occurrence, and perhaps prevent a few small tremors, could lead to the saving of thousands of lives and millions of dollars every year. In spite of their destructiveness, earthquakes have provided scientists with much new knowledge about the Earth's interior, leading to a better understanding of mountain building and continental drift.